In this video, like some of the chem major requested, we'll briefly introduce and talk about Raman spectroscopy. Unlike IR spectroscopy, Raman uses actually UV as a light source, and it has been discovered a long time ago, like early 1900s, 1920-ish, I think. The Raman is actually complementary to the IR spectroscopy, although Raman still observe vibrational modes. I will briefly mention why is the case later, but it's due to the difference in the principle how the method is working. And I'll show you the spectrum to make sure you understand what do I mean by complementary. Then sample prep is much easier for Raman. You don't need to do anything almost. And also sample can be placed in the polar solvent like water. Therefore bio, farm, medical field, where the solvents are like water or blood or something like that, the strong intense signal of the infrared is not gonna come in the way, and screening some of the usual weak signals on the IR, so you can actually observe them in the Raman. Also, in order to get detected, Raman's selection rule is different, so the sample doesn't have to be polar. I mean, it could be polar, but it doesn't have to be polar, and the Raman picks up good signal of some vibrational mode from the nonpolar molecules as well. In addition, Raman needs no reference light. Also, it has a very high spatial resolution because the Raman, light source is a UV or visible light. So it is very good to apply and take a biological image and apply for microscopy. However, Raman tend to be having weak sensitivity because we are using the light from scattering, so-called Raman scattering. So you need to use enhanced Raman spectroscopy for a lot of cases. Here are the spectra, FTIR spectrum and the Raman spectrum, and this 3000 area for sp3CHs. They're pretty similar, right? I mean, it's not always the case, but most of the time. And then the CO double bond carbonyl groups, they're intense in IR, but it's not necessarily intense. This time it came out very small. And then some carbon-carbon double bond stretching. This one I think we mentioned earlier, the symmetric vibration of the ring, this mode. Say it was a weak here, but it can come out as a big in the Raman like this, and this one stronger than Raman IR, and but this small one can show as a bigger signal, and so on. As you can see, there is some complementary signals, right? So this is basically some compound with a carbonyl group and alkene functional group. Looks like the carbonyl is conjugated with a double bond because the number is quite low as a normal carbonyl group. The second example of IR and the Raman is the amide compound with this functional group. And as you can see, you have an NH signal on IR, very intense. And you have a carbonyl that's conjugated with a nitrogen, so somewhat less than 1700. And that's strong. However, on the Raman, the NH, the strong peak became pretty small. And then the CO double bond again became small as some of the stretchings of the other signals became intense. That's showing the complementary properties of these two to each other. And here another biosample. You have a bipeptide, phenylalanine and the tryptophan. And as you can see, you have two similar benzene ring, and you have alcohol OH and the carboxylic acid functional group. So in regular IR, you have a very broad peak, and there obviously you have a carboxylic acid OH, but also the phenol type of OH, regular OH embedded here, but there is no way you can tell. And all of the sp3 or sp2 hydrogen stretchings are buried under OHs. And here very busy with the carbonyl groups, couple different carbonyl groups, and a lot of carbon-carbon double bonds, and even CN double bond. There are partial double bonds there, right? And a variety of the busy signals coming in. And if you think about multi-oligomeric peptide chain, it will be much busier. So for IR study, it's very difficult to keep track of what's happening to the functional groups, or say this particular ring is interacting with the enzyme or something. You cannot see the changes easily. But because the Raman is not really broadening due to the interaction or polarity, as you can see, you see the OHs of the two different hydroxyl group from the alcohol or carboxylic acid. You can see the difference, and if something happens to one of the OHs, and the shift will happen during the bioprocess, you can notice obviously. And then you also can notice what's happening to the sp2CHs and sp3CHs. Also, the carbonyl groups got weakened. Therefore, you start to see other signals, which is the carbon-carbon double bond, and you have a chance to differentiate which benzene ring belongs to where. So if something happens to one of them, then you can keep track of them with the Raman better. So you can see very definite advantage of the Raman spectroscopy over IR for certain cases. So why the IR and the Raman shows this difference? Let's really briefly talk about the principle. As you know, the IR infrared spectroscopy, we give IR regular. Either it is a continuous wave, CW, or a laser pulse. You give it, and then light will be interact and absorbed fully and partially. Then light come out of the sample. Then we do something over here, depends on what you need. Even you can do Fourier transform. Then you detect, basically. But when you give light in the Raman machine, the machine look fairly different also. It's about same size of box, but the compartment and the arrangement of the units look quite different. Anyway, when UV or visible light is given to the sample is coming in all kinds of states, right? Natural state, and it's pretty simple. It doesn't have to be a very controlled way. And then the UV will be absorbed, and we are not detecting what is absorbed. But instead, after absorption of the photon, the electron goes to the higher energy level, not vibration, but electron in the bond, okay, will go to the higher energy state. Then it'll come down and emit the photon. So instead of absorption, we are measuring by measuring out the transmitted light. But what we are looking at here is absorption, yeah, but what we are measuring is the emitted light emission, or the phenomenon can be called scattering, okay. But I like this word better. So light is actually absorbed, and then instead of caring about what wavelength of light is absorbed, we are checking what wavelength of light is coming out. Okay, so the original light is not what we are measuring. The light will be completely changed to the new frequency, new wave, and it will come out all direction. So to minimize the interference of the original frequency, because we don't want to measure that, unlike the IR, we place the detector perpendicular to it so we can have a maximum orthogonality to have a minimum interference, because quantum particles do not communicate with a 90-degree angle. So we detect what lights are coming out. That must be, including some different wavelength. So you know these Morse curve, the ground state electronically. For example, if you have a double bond, the pi electron is in the pi bond, that situation. And this has vibronic modes. So as you vibrate, the electron energy changes, right? So depends on the vibronic mode, the actual potential energy of the electron in the sigma bond, although the average distance of the bonding stays the same whether you are at the vibration 0 state or more vigorous vibration first and second state, doesn't matter, right? Average bonding distance is the same, but the variation becomes more and bigger. But as that happens, the energy is going up, potential energy is going up for the electron according to the vibration. However, most of the vibration will be around the ground state one. Depends on temperature according to the Maxwell distribution. You can use the formula and calculate, but most of them are here. Little population will be in the higher vibronic modes, and even less will be there, and so on. So when you give light to do measurement with the Raman machine, the majority of the molecule in the sample that's here in this vibration state with this much of a potential energy, whatever the number is, they get excited. But we are not exciting to the electronic excited states up here, like first electronic excited states, meaning you break this bond partially and bring one of the electron in the pi star orbital here, right? We don't do that. What we do in the Raman spectroscopy is we send the electron in the virtual state. Quantum mechanically, the state doesn't exist. That's why they cannot stay here. So we don't give this much of an energy. We give this much of energy using the visible light. That's why we are using visible light. IR light will only give enough energy to promote them to here sometimes. this state live long enough to absorb second time photon, then you can go there, and that's what we call overtone, right? So the virtual state is almost like it's not the electron in the pi orbital, not in the pi star, which is up here. So you almost like having electron disturbed by high energy light, right? And they are nearly going there, but not quite, and they're coming back quickly. That's what we are doing. So the electron in the lowest vibronic mode, which is a stable electron, you disturb them, so the electrons are moving more vigorously with a more angular momentum, and it's going up in the energy, meaning they are getting promoted partially, but the energy wasn't enough to go and reach the quantum state of pi star orbital, so they come back, because that is not a permitted state. So it comes back down. Okay. And there will be some low concentration of the V1 state electron, meaning electron still in the pi, but CO bond is vibrating more, and that's less probable. If you raise the temperature, you can make the more bonds vibrates and get into the V1 state. But yeah, but generally speaking, in the room temperature, say we have less population getting energy and reach the virtual state and comes back down here or even there. Okay. And also you should know that it could come down here when you excite from there, but like I mentioned here, it may also end up coming down here or just there by emitting photons. Okay, so this photon and this photon, they possess less energy than the original energy that we used. So let's just say the original energy we used here, that frequency was h nu, that frequency, for example, of the Planck energy equation, right? Then you know this, this energy here that reaches the original state, that will be identical, right? So you absorb such amount of energy, you come down and spit out same amount of energy photon. That can happen. Or it can happen that the virtual state go down, electron in the virtual state go down to the higher vibronic state, and even higher energy state. Let's label them as a B1, H nu 2, H nu 1, H nu 2, and frequency wise, most frequent wave, and then little less and somewhat more less, so less energy came out. However, eventually though, all of these states will have to release heat energy and come down to the most stable vibronic state. That's the most stable state for them. So there will be heat emission. So when you keep shooting UV to the sample, you have to know sample in the machine gets warmer and warmer. Therefore, if you run the experiment with the Raman too long, then you end up populating more sample over here, and your data is not gonna be same as the initial one. Therefore, I can show the detected wavelength V, right? The light that came out when it's coming down, V. Then the one that came down to the second vibronic state, the third one in the order, because the energy is less, and then even more less energy frequency. But we can also imagine the case over here. It could go up from the second vibronic state, but it can come down to the lower, even lower vibronic state. So sometimes you can see that you are getting more higher energy light coming out than you gave. Okay. So you can show something like this. More than original light, you have higher frequency, and even higher frequency energy light can come out. Okay. So in terms of intensity wise, this peak that spit out the same amount of the energy from the given vibronic state will be the most intense, usually very, intense. And then other peaks that's reaching to other states, they're normally less likely, so weaker. There is some quantum region. If you adopt the wave function and then solve wave function, then you can figure out the intensity. However, yeah, I'm not gonna get into that here. So these are weaker, and also, as you can see, this side is a little stronger than this side, because this side is from the most populated one. And say if the whole thing is observing the vibration from here to virtual, right? Then coming down here is most likely. Then this is less likely, and even giving out more is even less likely. You emit this same amount of photon compared to the given energy. That's most intense. That's V. Okay, that's like a V1 and V2. That's like a V3 and V4. So we call this as a Rayleigh scattering, and this is Stokes, the one that has less energy frequency, right? Those are the one coming down to the higher vibronic state compared to the original one, and the anti-Stokes is the one that comes down to more stable one, so it's emitting photon that has more energy in that anti-Stokes that is less likely. So Stokes is more intense than the anti-Stokes peaks, but they are both much weaker than Rayleigh scattering light. Also, we know that the energy gap between this and this is the energy between these, right, vibronic states. So we call this as a Raman shift. Here as well, Raman shift. But you recognize this number if you calculate the delta V. You can calculate the energy, but that value is corresponding the energy between these vibration states. As you can see, Raman spec is very clever. it's really a clever way of extracting the data of the vibrational energy, while they're not really exciting vibrational directly. But because of that, you know that the photon is not interacting with the dipole. So you can get away from this dipole related phenomenon that's happening on the IR spectrum. And as you know, the dipole moment is normally is the like a vector expressed as x, y, or z, like this, right? So charge times distance, and the distance and the dipole moment can be vector, but the vector can be expressed, by the linear combination of just x, y, and z. However, here you are moving electron. The movement of the electron has to do with the whole area where the electron is in the molecule. So it has to do with the molecular orbital. As you move electron from one molecular orbital, you are moving electron density in a certain area of the molecule instead of x, y, z linear component. Therefore, the Raman spectroscopy, the selection rule is not like the IR case where the extinction coefficient, if you remember, was square of the dipole moment that's proportional to the absorptivity. But in the Raman, dipole moment is proportional to this electric field. We are giving electric field, right, with the light. Then we are inducing this, which is polarizability. How well you can polarize the molecule, meaning how well you can move electron from the most dispersed way to more polarized way. So whichever the molecule is easy to get polarized, it's giving stronger signal in the Raman. Unlike the IR, whichever vibration is making bigger changes of dipole moment, x, y, z. But polarizability has to do with area. Sorry about that. I was going out of the window again. Okay, I have only a couple minutes left here. So if you remember our discussions with the IR, all of these atoms, right, carbons and hydrogens, and the carbon with the 3 hydrogens, all of them, each atoms in the molecule can have 3 modes of movement, right, x, y, z. So sometimes the random XYZ movement of the each atoms in the molecule make the molecule tumble or translate from one point of the coordinate to the other. We don't count, but some of the movements collaboratively have a certain vibration, right? It could be stretching, it could be bending out of plane or rocking, whatever. So using all those movement vectors, if you have partial charges there and there, you have charges moving around. That's how we eventually, if you're chem major, we're gonna have to find the point group of this molecule, so you can relate their motion into these symmetry elements. And then if you look at the each point group table, the irreducible representation table, you are finding these things. Let's skip all the calculation part, but when you see the symbol, certain motions, I think at one point I mentioned it has a certain symmetry element, like say certain motion of vibration was A1, then you can say, oh, that A1 vibronic modes will give you dipole moment change in the z-axis, right? But certain, mode of the vibration will not give any xyz. In that case, you can say the one that has xyz component, they are IR active, okay? But the one that does not have xyz vector components, then this modes of vibration is not IR active. However, that motion happened to be x times y. If you multiply x times y, you get an area. So it will be now Raman active. So as you can see, all of these have area concept, right? So they are Raman active modes. Whatever the vibronic state is giving this type of symmetry. And how do you know a certain vibration has this or this type of a symmetry? Then you should know how to read these numbers in this table. But that's out of this class's scope. I hope I can do that later with the other series of video for upper level chemistry. But I think this should be more than enough for sophomores if you are getting ready for upper level chemistry courses, analytical, quantum, or instrumental. This is giving you certain connection with orgo to those classes. I hope this is helpful, and I'll see you later.